Because we use sample data to try to understand how a treatment would affect a population, as researchers, we seek to tease as much information out of our sample data as we are able to sharpen our understanding. Another supplementary procedure we use is estimation. The goal of estimation is to determine the value of the population mean after treatment. Estimation is used to find out how much treatment effect there was, the size of the treatment effect, or to identify an estimate of the population mean. You will learn two types of estimation: point estimation and interval estimation. The basic principle underlying all of inferential statistics is that samples are representative of the populations from which they come. The most direct application of this principle is the use of sample values as estimators of the corresponding population values. That is, using statistics to estimate parameters. The use of a sample to estimate a population is quite common. At the heart of the inferential hypothesis testing logic is our goal to estimate as precisely as possible what the population parameters would be if we were able to give our treatment to all the subjects in the population. Because we are unable to do that, we tease as much information as we can from our sample data to create as clear a picture as possible of the population parameters. We estimate the population parameters in two ways: point estimates and interval estimates. Point estimates have the advantage of being very precise. They specify a particular value, the mean, or M, of our sample, which we use as our starting point. The second type of estimate, or interval estimates, use a range of values that we create and that bracket the mean, or M. Interval estimates do not have the precision of point estimates, but they do give you more confidence that the actual treated population mean is located within that range of values. Because the interval estimates are associated with confidence, they usually are called confidence intervals. Estimation is used in the same general situations in which we have already used hypothesis testing. So to recap, the goal of the estimation process is to identify as closely as we can what the actual treated population mean, or mu, value is with the sample data we have available. On the slide, you see the formula for calculating a confidence interval estimate for the single sample t-test. We start the estimation process by identifying the point estimate, which is the sample mean, or M. It is a precise number, but we can't be very confident how closely it approximates the treated population mean, or mu. So to create a confidence interval, to the M, we will both add and subtract the product of a critical t-value that we will locate in the t-table multiplied by the standard error. The selection of the critical t-value is related to the percentage of confidence with which we want to compose our interval. So if the goal is to calculate a 95% confidence interval, then we will select the column from the two-tailed row for an alpha of 0.05. If the goal is to calculate a 90% confidence interval, then we use the 0.10 alpha. For a 99% confidence interval, the 0.01 alpha. For confidence intervals, you always use the two-tailed row. We calculate degrees of freedom the same way for confidence intervals as we do for a t-test. On the Blackboard course site, posted near this video, you will see a document entitled Chapters 9 to 11 T-Test Handout. Print that out as it summarizes the formulas you will be working with in Chapters 9, 10, and 11. There are two things that will influence your confidence interval formula: percent of confidence and sample size. To gain more confidence in your estimate, you must increase the width of the interval, for example, from 80% to 90%. Conversely, to have a smaller interval, you must give up confidence, for example, 95% to 90%. This is the basic trade-off between precision and confidence that was discussed. A bigger sample gives you more information about the population and allows you to make a more precise estimate, resulting in a narrower interval. The sample size controls the magnitude of the standard error in the estimation formula. As the sample size increases, the standard error decreases and the interval gets smaller, which means you will have a narrower range of values that bracket your sample mean. Finally, estimation can be used to get an indication of the significance of the effect. You should recognize that a mean difference of 0 is exactly what would be predicted by the null hypothesis if we were doing a hypothesis test. You also should realize that a 0 difference is outside the 95% confidence interval. In other words, 0 is not an acceptable value if we want 95% confidence in our estimate. To conclude that a value of 0 is not acceptable with 95% confidence is equivalent to concluding that a value of 0 is rejected with 95% confidence. This conclusion is equivalent to rejecting the null with an alpha of 0.05. On the other hand, if a mean difference of 0 were included within the 95% confidence interval, then we would have to conclude that 0 is an acceptable value, which is the same as failing to reject the null.